So here's an example chi-square practice question. This one isn't couched in genetics terms per se, and I'm going to calculate this by hand instead of using Excel or Google Sheets. So imagine somebody says they've got a bag and they've put, say, 20 different balls of 2 different colors, and they say that they've put an equal number of red balls and blue balls. They tell you this, but they don't show you the bag. So we're going to have 10 of these they claim are blue, and the other 10 are red. So one thing you could do to test whether or not this is true is draw a random sample, put your hand in the bag, and you pull out some number of balls. So let's say you pick out 7 balls, and 2 of them are blue, which means the other 5 are red. The question statistically is it possible that if the person that put the balls in the bag was telling the truth and there really are an equal number, 10 blue and 10 red, is it statistically likely that you would randomly, if you pulled out 7, get 2 blue and 5 red? 2 and 5 doesn't seem like they would come from an equal number of red and blue balls in a bag that you could draw from. But it's possible that by chance you just happened to pick more red balls than blue balls. So the chi-square test is what we would use to assess this. In this case, our observation, we have 2 categories. We've got number of red balls and we've got number of blue balls. And then we're going to have our expected values. And somewhere here we should have a total or a sum. So we had observed 5 red, 2 blue. That's a total of 7 observations. And note that we have 2 categories, red and blue. So the number of categories is 2. And we need to know that to calculate the degrees of freedom later. Number of categories equals 2. And in a chi-square test, the number of observations has to equal the number of expectations, or the expected number of draws of balls from the bag, for example. Because, in this case, the person that filled the bag claimed that it was an even number of blue balls and red balls, then our expectation should be we'd see an equal number of red balls and blue balls when we draw them. So if we divide 7 equally, that's twice 3.5. So we should observe, if the person's claim is true, and this is the null hypothesis, that there are an equal number of balls, 10 and 10, that sets our null hypothesis, or our expectation. So how to carry out this chi-square test? We have the observed number of red balls minus the expected number squared, divided by the expected number. So that's the term for the category of red. And we have to have a second term or clause for every category. So in this case, we've only got one more category. That was the number of blue balls in the bag. So that would be observed, we saw 2 minus the expected number, 3.5, squared, divided by the expected number, 3.5. And it's important to note that these numbers that I'm putting into this formula come from this table. The observed number of red, 5, and the expected number of red, 3.5 and 3.5. It's not necessarily always the case, although it will often be the case in genetics, that the number of expected values are the same. We'll see an example where that's not the case later in the semester. So then, the numerical product of that equation is what we call the chi-square test statistic. And this chi-square test statistic is approximately 1.29. The number of degrees of freedom we have is the number of categories, which was 2, minus 1, so the number of degrees of freedom is 1. And with these two pieces of information, the number of degrees of freedom and our chi-square test statistic value, we can use a chi-squared p-value table, which I'll add to the next slide, to interpret what these mean and whether that is a statistically significant difference. That is the observation of 5 red, and 2 blue. Is that statistically significantly different from what we would have expected, which is to draw 3.5 of each? So here's our chi-squared table. And remember, our chi-squared value was approximately 1.29 with degrees of freedom equal to 1. So we look in the column here on the left until we find the row that has the number of degrees of freedom that we're looking for. So degrees of freedom is 1. So we're going to be focusing entirely on the top row of this chart. And the values that are in this row are the chi-squared values. So what we're looking for is a place where we see 1.29. We probably won't find that number. It's going to land in between two of these numbers. So 1.29 fits right in there between 1.0742 and 1.6424. So the interpretation then is we need to look at the header. The top row here says p-values, these numbers in bold. And so because this chi-square test statistic value falls in between 1.07 and 1.64, we look up into the header, that top row. Those are the p-values, the probability values that flank the real p-value, whatever specific p-value is associated with 1.29, which is in between those two numbers, is in between 0.3 and 0.2. So in this case, the p-value associated with this chi-square value is less than 0.3, but it's also greater than 0.2. So this is what you'd report the p-value as if you use a chi-square table. If you use Excel or Google Sheets, you can calculate the exact p-value, not a range, but just a single number. That is the p-value. Lastly, to interpret, p-values less than or equal to 0.05 are indicative of data that are statistically significantly different. And in our case, the p-value is greater than 0.05. So statistically significantly different if the p-value is less than or equal to 0.05. Our p-value is greater than that. It's between 0.2 and 0.3. So the final interpretation is the observed and expected values are not statistically different. In other words, having drawn a small number of balls from a large bag of balls, not statistically significantly different, means that there's a reasonable probability that by chance we happen to draw more of one color ball than the other. And so this is a really important point for scientists because it makes us understand that the more samples we get, the more times we drew balls out of the bag, the more likely we are to arrive at a true representation of exactly how many of each colored ball is in the bag. Of course, if we took all the balls out and we counted them, we would know for sure. But there are a lot of things in science where we can't measure everybody or everything. We have to take a sample and then draw conclusions from a sample. So the chi-square test tells us whether or not the sample is or is not statistically significantly different from our hypothesis, our expectation. And I should probably amend this because it's not statistically significantly different. There we go. Here's another example of a potential use of the chi-square test. Let's say we have this 20 nucleotide sequence, and for example, we might want to know if this sequence came from random nucleotides. In other words, is the expectation that if you have 20 nucleotides of DNA, then there would be, on average, 5 Gs, 5 Cs, 5 Ts, and 5 As. And what we can do is to use a chi-square test to compare the observed numbers of G's, A's, C's, and T's to this expected number. And that would test the null hypothesis that this is a random bunch of nucleotides, 20 nucleotides, that are not statistically significantly different from this expected ratio. So in this case, we just have to count up the observed numbers of nucleotides. That's 9 G's. Seven C's, 2 T's, and 2 A's. And then double check to make sure that all those also add up to 20. And then we can set up our chi-square analysis with, I'll just do one example with G. Observed minus expected squared over expected. And that equals 3.2. And then you do the exact same thing, observed minus expected squared over expected for C, and get that value, the same for T, and get that value, and the same for A, 2 observed, 5 expected. And you add up all of those numbers, so plus the same value for C, plus the value you calculate for T, plus the value you calculate for A, and that gives you the chi-square test statistic value, which in this case is 7.6. And in this case, we have 4 categories of data, A's, T's, G's, and C's, which means our degrees of freedom is number of categories minus 1 equals 3. So again, we have the 2 pieces of information we need to interpret these data and identify the p-value associated with these numbers. And what I did this time, instead of using the chi-square table, was I used Google Sheets or Microsoft Excel by typing the following into the equation bar: equals chi-dist, short for the chi-square distribution, open parentheses, whatever the chi-square value is, in this case 7.6, and then a comma, and then type in what the degrees of freedom is, 3, close parentheses, and then hit enter. And the present value in the cell after you hit enter will be the p-value, which in this case is 0.055. And once again, this value is greater than 0.05. So the result here is that there's no significant difference between the observed and the expected values. In other words, and this may seem counterintuitive, but this is why we have this statistical test, because it gives us an objective measurement of significant differences. You might have imagined that seeing almost twice as many G's than expected, and half as many A's as expected, and twice as many T's half as many T's as expected, and so forth, would be significantly different. But this test tells us that it's not, that there's only a very small chance, less than a 5% chance, which again is what the p-value less than 0.05 means. This indicates, roughly, that there's about a 5.5% chance that these numbers really are from the observed numbers, that is, are really from a non-random DNA sequence. So there's still a chance, if we wanted to support the hypothesis, that these really do come from a piece of DNA that has a non-random DNA distribution. But the chi-square test tells us that it's really unlikely, given what we've observed, that that's true. There's no significant difference between the expected and the observed values.